We are now going to look at making decisions between two assets, and in particular, how much of two assets are we going to put into our portfolio, or what proportion of each one of these two assets will we put into each one of our portfolios. This is our example portfolio problem with two assets. We'll expand it to more assets in a module next week. Putting assets into more than one asset, so in our case it's two, increases risk efficiency in general. And risk efficiency just means that we can get the same return for a lower standard deviation, or stated another way, for the same standard deviation you can get a higher return. That is risk efficiency. We assume that you want to have higher returns and lower risks. So combining two assets, we can increase risk efficiency if those assets aren't perfectly correlated. The material that we're going to go over in this model is also covered in Goatsman, Chapter 1 and 2, which is the readings assigned for this week. So take a look at those, Chapter 1 and 2, and that will discuss risk efficiency, and making asset decisions in a portfolio context. Here is the decision problem that we're looking at. We have two assets, and we can make an investment in one of them, or the other one of them, or in both of them. We'll add more than two assets next week so that we can have many assets. Let's say, bullet point 2 there, is that or second bullet point, we have $1,000 to invest and can invest in two assets. All you need to know, bullet point 3, about the future returns of those two assets is given by the mean, standard deviations, and correlations between those two assets. And actually, in the case of two assets, there's only one. There's a correlation coefficient. So it's a correlation coefficient between asset 1 and asset 2. We're in particular making some strong assumptions here. We're saying that those assets are distributed symmetrically, most likely normally. We know the mean, we know the standard deviation, and we know the correlation coefficient between those two assets. How much then, last point here, is how much should we invest in asset 1 and asset 2? And again, you could invest all of it in asset 1, you could invest all of it in asset 2, or you could invest a proportion in asset 1 and the remaining portion in asset 2. So that's our decision, how much to invest in each one of the assets. This setup is a prototype of all portfolio props. You have an amount that you want to invest. How much should you invest in each asset? Again, next week we're going to look at a framework where we can look at this in a multiple context. So that's where we're going to. This week it's only one asset. In making those portfolio selections, what we have to know in order to make that selection is investors' preferences. And what we can know about investors, or what we assume about all investors, is two items that are listed at the bottom. Investors prefer less risk, which we're going to measure by the standard deviation, and investors prefer more returns, which is the expected, or which will be given by the expected return. This graph that you see here has two axes on it. The horizontal axis is given by standard deviation. So here's where we're going to put the standard deviation of those returns of those assets, and the vertical asset is expected return. In the middle of this axis, you see indifference curves. You see 4 of them: A, B, C, and D, and these are individuals' preferences for risk. A is the lowest indifference curve, or there's less utility on this curve than there is on B, than there is on C, and there is on D. So these indifference curves, for example A, an individual would be indifferent between different assets along this curve that had those trade off between the expected returns and standard deviation given on those indifference curves. Again, what we're going to assume here is that people prefer more return, and let me just illustrate that with this green line that is now showing up on this axis. This axis, as you go up the line or move up the line, you increase return, and as you can see, if you increase return for the same standard deviation, which again is what happens along that green line, you move up the indifference curves A, B, C, and D. So this, in this case, the individual is gaining utility as we increase return. The same thing happens when we hold the standard deviation constant. So this green line now shows the standard deviation expected return held constant and increasing standard deviation. So as we lower the standard deviation or move to the left, we increase utility A, B, C, and D. So as we move along this one to the left, we increase utility. The exact shape of those indifference curves is something that's specific to the individual, but we do know that as you move up and to the left on this chart, you will increase the utility of that individual. Now let me introduce some return notation and how we're going to describe the returns in our two portfolio model. And actually this will be the case also when we move into more assets as well. This mu I is the expected return from asset I, so we'll have two of these, mu1 for asset 1, mu2 for asset 2. We also have the standard deviation, sigma I, for the standard deviation for asset I. Again, we will have two, 1 and 2 sigmas. We also have the variance, and the variance is the standard deviation squared. We also have, finally, a correlation coefficient, and there will be one of these when we have two assets, one between asset 1 and asset 2. This is the correlation coefficient. That correlation ranges from 1 to -1. It has to be be between 1 and -1. One item of note here is that mu, sigma, and the correlation coefficient, which is given by the Greek letter rho, are denoted by Greek letters. We do this for a very specific reason, and that is because they're quote-unquote true. We know what these are. We assume that we know what these are. We will talk about this assumption more as we go through, but right now we're assuming that we do know what our expected return, standard deviation, and correlation coefficient is for these assets. The key to whether and the extent to which we have diversification is the correlation coefficient. That correlation coefficient can range from 1 to -1, and from a risk efficiency standpoint, what we hope is that is a very low correlation. The lower it is, the more we can reduce the risk for a same level of return. I'm going to give you an examples in the next 3 slides what returns would look like for different correlation coefficients. I'm going to give the two extremes, 1 and -1, and then we'll look at something sort of in between those, 1 and -1, just to give you a feel for what that correlation coefficient means. Here are two assets that have a correlation coefficient of 1. And let me describe what's going on in these graphs. You have time on the horizontal axis, 1, 2, 3, 4, 5, 6. So each one of these graphs has 6 time periods. The blue line is returns from one asset, and our asset in blue asset in time period 1 has a 0.4 return, 0.4% return, or 40% return, excuse me, in time period 2, 20, and it just bounces back and forth. 0.4, 0.2, 0.4, 0.2, 0.4, 0.2. The red line is another asset. It has lower returns than the blue asset. It goes from 0.3 to 0.1, 0.3 to 0.1, 0.3, 0.1. These two assets have a perfect correlation, and I'm looking here at the upper left hand graph. They are perfectly correlated. They move in lockstep with one another. When one goes down, the other one goes down. When one goes up, the other one goes up. The upper left corner is an extreme case. You can also have something like in the bottom right graph. These two assets have the same upper return, but their lower return is the blue asset goes down more than the red asset. They are still correlated and have a correlation coefficient of 1. The key point here is that when a correlation coefficient equals 1, when one asset goes down, the other asset goes down. When the one asset goes up, the other asset goes up over time. Now let's look at the case when the correlation coefficient is -1. Here, and let's start with the upper graph to the left, we have two assets again, blue, red, and time, 1, 2, 3, 4, 5, 6 time periods as indicated on the horizontal axis. Blue in time period 1 has a 0.4 return, red has a 0.2 return. Now, in time period 2, blue has a 0.2 return, and our red asset goes up to 0.4. And as you can see, they cross or react exactly opposite of one another. So, in this case, both of these would have a mean of 0.3 over the time period, but they move in exactly the opposite manner. So, as when the blue asset goes down, the red asset goes up. Blue asset goes up, the red asset goes down. This is perfectly negative correlation. And as you can see here, that is an asset 1. Actually, if we had 0.5 weight on these two assets, we would have a 0.3 return, or a safe return over the entire time period. Bottom right graph gives the same, assets that are perfectly negatively correlated, but with less extremes. They just move in opposite directions from one another as those assets move. Now I'm going to give a little different view of correlation coefficients, and let's take the upper left graph, which has labeled as the correlation coefficient of 1. All three of these graphs have two assets shown in them. Asset 1 would be the horizontal axis, asset 2 would be the vertical axis. And what I did here, was array the returns of two assets, given that they're both mean at 0.1, standard deviation of 0.05. So both of these assets have the same expected return and same standard deviation. What I then did was array the returns, given that they're perfectly correlated in the upper right hand axis. Given that both of these axes has the same return and same standard deviation, correlation coefficient of 1, if one has a 0.1 return, the other one will have a 0.1 return, and you can see that there will be a straight line. Go to the bottom left axis and you'll see a negative -1 correlation. Here they move in perfect opposite one another, and you can see that they go down in the same proportion. The graph to the right with correlation coefficient equal to 0 shows when there is no correlation between those two assets, and you can see here that's just a scatter of returns. Asset 1 return bears no information that you can use to tell what asset 2 returns look like, and it's a scatter. Now, if you take the upper right and graph and has a correlation coefficient of 1, as you move it to correlation coefficient of 0, that graph will move from that straight line. It'll become a cloud around 1 and then eventually go to 0. Then as we increase or decrease the correlation coefficient from 0 to -1, the graph will begin to look more like from the correlation coefficient graph of 0 to the correlation coefficient graph equal to -1. So this just gives you a feel for what correlation coefficients look like in what their returns would look like. We are now moving closer to the point where we're going to look at making portfolio choices, and I'm going to use two specific assets here. Asset 1 has a 0.04 return, expected return, and I'm going to call it T-bills, 0.04 return and a standard deviation of 0.06. Stocks, asset 2 has 0.11 return and a standard deviation of 0.25. Correlation coefficient between these two assets is 0.6. This is the two asset case, and the portfolio case only works in the two asset case if one asset has both lower returns and lower standard deviation. If that were not the case, and one return had a higher return and a lower standard deviation, that would be preferred by all individuals. Put that on a graph. Look at the indifference curves from our previous case and you will see why that is the case. Note that when we move to multiple assets, that won't necessarily be the case, and we'll talk about that when we get there. But for our examples, we're going to use numeric examples. We're going to use these numbers. Asset 1, the low return, is going to be called the T-bill asset, and asset 2 with the higher returns and higher risk is going to be called the stock return. Now I have the two assets. I've told you what their returns are. Our portfolio problem is determining how much to put in asset 1 and asset 2. We are going to denote the decision variable equal to W1. W1 is a proportion of total investment to invest in asset 1. So W1 is going to be a number between 0 and 1. If it's 0.1, that means we're investing 10% in asset 1. If it's 0.2, we're investing in 20% in asset 1. If it's 0.9, we're investing 90% in asset 1. All of these assets all of our funds have to be invested totally in the assets. So W1 plus W2 in our two asset case has to equal 1. All funds have to be invested. So that's given by the red line there, or red numbers there. W1 plus W2 equals 1. And note that that implies the blue equation. Our amount that we invest in asset 2 is 1 minus W1, or what we invest in asset 1. This problem only has one decision variable. If we invest 10% in asset 1, by definition we're investing 90% in asset 2. If we're investing 90% in asset 1, we're investing 10% in asset 2. Given what we've laid out, we can now indicate what our portfolio returns are, and that's going to be shown on the next slide. We're going to show what the mean, standard deviations, or variances are of portfolio returns. These are what we're going to show on the next slide, statistical equations, and they're not dependent on the portfolio theory themselves. These are just linear combinations of two random variables. It's a statistical relationship. Any random variables that are combined in a linear fashion will have these relationships. Another point is that if each one of the assets is distributed normally, each of the portfolio will be distributed normally as well. Here then are the means and standard deviations of our portfolio. And again, this is looking at our portfolio. First equation gives the expected return. Second equation gives the variance. The expected return of our portfolio is the weighted average returns from each one of the assets. So our portfolio return is the proportion invested in asset 1 times its expected return plus the proportion invested in asset 2 times its expected return. There's nothing magic here. We just get the weighted average of those two asset returns. Second equation shows the variance of the portfolio, and here the variance equals the weight of the first asset squared times the variance of the first asset plus the weight of the second in the second asset squared times the variance of the second asset plus the cross term. 2 times weight 1, weight 2 times the correlation coefficient times the standard deviation 1, standard deviation 2. The correlation coefficient, and you can do this if you want to look at this for yourself, as that correlation coefficient goes from 1 down, the variance of that portfolio will become less. If you make that correlation coefficient negative, it actually reduces you can see that it becomes a negative term and reduces the variance of the portfolio. Just as a note, the standard deviation is the Zoyce case is the square root of the variance. What we're going to do is now use those two numbers, the mean and the variance, and we're going to implement them in an Excel spreadsheet so that we can see what happens as we look at add assets or have two assets in our portfolio. We're now back in Excel. We are in the Week 2 GeoMeans Return and Portfolio Microsoft Excel spreadsheet, which you can get by downloading from the Compass website. We have here two assets, Asset 1, Asset 2. Asset 1 is T-bills in our example, and Asset 2 is stocks. Asset 1 has an expected return of 0.04, standard deviation of 0.06. Asset 2 has an expected return of 0.11, standard deviation of 0.25, and the correlation coefficient between those two is 0.6. I currently have a weight in here of 0.5. Asset 1 has a weight of 0.5. That means that Asset 2 also has a weight of 0.5. Over here we have the expected return calculation given a 0.5 weight in Asset 1. And the formula for this is, as given on the previous slide, expected return for Asset 1 times its weight, expected return Asset 2 times its weight. Just to show you, here's 0.075. If we put all of our weight in Asset 1, we have 0.04 mean, which is exactly the same as Asset 1, and obviously the standard deviation is the same as well. We put a 0 weight here. All of our weight is on Asset 2. We have a 0.11 return, 0.25 standard deviation. 0.5 is halfway between, and we get 0.75% return. Our standard deviation formula is given here, and you can look at the previous slide and look at here and see that it is the same calculation. Take the square root of it to get the standard deviation. One of the things that I want you to note here is this is a 0.145 standard deviation. As it turns out, this is less than if we take the average of those two. If we take them plus the weights, that standard deviation is 0.155. That it is less than 0.145 is what causes risk efficiency. We are getting a lower standard deviation by combining the assets, and we're getting that weight lowered. Now note, this is less because this correlation is less than 1. If I make this 1, the standard deviation will go to 0.155. Exactly the same. If you look at the formula, as we get closer to 1, it gets closer just to adding them together. I'm going to turn this back to 0.6. And again, as long as we have a correlation coefficient of less than 1 here, our standard deviation will go down. Let's put it at 0, and you'll see that that 0.145 will get less, 0.129. Let's put it back to 0.6. I'm going to erase this, which again, we're just taking the weights of those two. And our next slide will illustrate what's on this graph at the bottom. I am now going to illustrate the calculation of this graph. Now note a couple of things here. Standard deviation is on the bottom axis, expected return is on the vertical axis. This is the usual way we list portfolios or trade-offs. Standard deviation on the bottom axis, expected returns on the vertical axis. Exactly the same as how we showed the utility function. This blue line here gives different portfolios and a combination of those portfolios and the trade-offs that we can get between standard deviation and expected returns. This is actually a graph of these data points here. And what I did here was start out with weight of 0, W1, all the way up to 1. And that what that would mean is that W2 is the opposite of this. So this would be 1. Weight of W2 would be 1, 0.95, 0.9, 0.85. Here is our expected return calculation, and I did this as a table, just calculating those. If you look at this, right here is the mean, here's the standard deviation. I created a table that did those calculations, but if you put 0 in here, you'll see that this will turn out to be 0.25 and 0.1. Or excuse me, 0.25, same. 0.11, same. Now let's do 0.05. 0.05 has an expected return of 1.07, same as here. 0.239, same as here. Alright. We got a graph of here. And this is just a graph of this. You can see this if you want to. Insert a scatter graph, collect the lines. You get the same exact thing with some more formatting. So we've graphed this frontier. Now what I want to do is look at how that frontier changes as we change the correlation coefficient. Let's start with 1. Now note, 1 is just a straight line. If we have a correlation coefficient of 1, we gain no risk efficiencies. In essence, we can make linear choices between asset 1 and asset 2, and we'll get linear combinations of the mean and standard deviation of those. This line is going to bulge this way as we lower the correlation coefficient. Remember that as we move this way, our investors' preferences or our utility increases. We want more risk for lower standard deviation. So as we now watch that line, I'm going to put 0.9, bulges a little bit, 0.8, bulges a little bit more, 0.7, 0.6, 0.5, 0.4, 0.3. You see it's getting more and more. We're getting more and more risk efficiency. We're getting further and further away from that axis. 0.2, 0.1, 0 minus 0.1 minus 0.2 minus 0.3 minus 0.4, oops, minus 0.4 minus 0.5 minus 0.6. You see, and we want to always be here on this axis. We always want to be further. We're getting more risk reductions. And let me just keep going. Minus 0.7 minus 0.8 minus 0.9. Now I'm going to put minus 1 in here. As soon as I do that, watch what happens is on the expected returns vertical axis. We hit it. We are able, if we have minus 0.1 return, minus 1 return, we can combine those two risky assets and create a portfolio that has no risk because they have a minus 0.1 return. So you can see here we have a range of efficient frontiers that change with this correlation coefficient. The investor can't change that correlation coefficient, but the more negative it goes, the more risk efficiency we get. And again, as we back off from that, we're going to go back the opposite direction. And you can see it just goes back to our straight line. I'm now at 0.6. Alright, you can see here what happens to risk efficiency. You might want to change this graph, change some of these expected returns, change this correlation coefficient, and observe what happens to the EV frontier. And again, we would want to be on this frontier if we're making investments. Our risk efficiency, to summarize here, is increased with assets with correlation less than 1. We would like that correlation to coefficient be as low as possible. Obviously, we do not have any control over that. And our choice of assets will still depend on the individual preferences. Where we land on that line will depend on individual preferences.